Now I've just start record. Okay, so let's move on to dimension and units. All right. So what is the definition of dimension and definition of units? So dimension is actually what we call as any physical quantity that can be characterized by dimension. So if you look at the table down here, so dimension could be like length, mass, time, temperature, electric current, amount of light, amount of matter, and so on. Okay. And then there is what we call as unit. So unit is actually the magnitudes assigned to the dimension. For example, like if you have length, then you have meter. If you have mass, there is a kilogram. Time, which is in second, minutes, and so on. And if let's say it's temperature, you have Kelvin, you have degrees Celsius, you have Rankine, you have Fahrenheit. And for example, electric current, you have ampere, and so on. So those are considered as unit. And in SI units, for example, there is some prefix that we can use. Okay, for example, like in seconds, you can have milliseconds, you can have centiseconds, you can have microseconds, for example, and even in Kelvin. Okay, except yeah, of course, I've never heard people say mega Kelvin, right? But that can be a prefix towards the SI unit. um, like you can have like micro milliampere, for example, micro candela, nanomoles, for example, like nano kilogram, nanograms, for example. So those are the prefix that you can use. But clearly dimension is something that you can characterize. Okay, and then unit is actually the magnitudes assigned to this particular dimension. So as a classification of dimension, we have a primary and secondary. Okay, for example, like the mass, length, temperature, time, amount of matter, electric current, and amount of light. This is what we call as primary dimension. Okay, because it is not derived from something else. It is just as it is. Okay, mass is kilogram, length is meter, and so on. Secondary is what actually we call it as a derived dimension, derived from the primary. For example, like volume is actually the length multiplied with a length and multiplied with another length. So you got the volume. How about velocity? Okay. How about energy? So you need to figure out yourself. How does this being developed from different primary dimension? So it is being multiple. Okay. And then it becomes what we call a secondary dimension. So in this case, in the unit itself, they have three type of unit system. One is what we call as metric SI system, which is in meter, kilogram, and second. And then you also have what we call as American Engineering System, AES, where you have a slightly different units, okay, which is in foot, inch, pound mass, okay. Pound mass is LBM, pound mass is LBM. And then you also have second, which is also similar with this one. And then you have CGS, centimeter, gram, second. This is also another system. So why do we have different system? I do not know. Okay. Some, for example, like the US like to use AES in the system. Even actually the British, they use slightly I think they use like BTU. They most of the time they are using as well this unique American unit. But as the standard international, most of the time we are using meter, kilogram, and second. So you will be encountered from time to time when you work later or even now after this. You will encounter actually different unit. For example, like you have a 1 kilogram with and then another unit with 1 inch, and for example, like people ask you what is your height, for example, and then they say my height is 5 feet. Sorry, 5 feet 7 inch, for example. Okay, and then you need to convert those into SI. Sometimes we do not know what is SI, so we need to learn about the conversion, right? We need to convert it into our own. We need to learn about the conversion. So this is where actually some conversion helps. Of course, right now it is much easier. If let's say you just type it in Google, you'll be able to convert everything, right? But you need to know where does it from. For example, like here, if you have a length with 1 meter, this is also equivalent to 100 centimeter. This is also equivalent to 3.28 feet, also equivalent to 39 inch. Okay, so this is AES unit. if let's say you have mass, for example, 1 kilogram is equals to 10 to the power of 3 grams, and it is 2.2 pound mass. Okay. For force as well, so you have uh, okay, you have a different unit, 1 kilogram meter per second, and then it's also being converted into 10 to the power of 5 dyne, right? So dyne is actually what you can get from here lah. This is not being given 10 to the power of 5 dyne. And then different unit as well for pressure. So you can see that a lot of the times and the pressure is very they have a lot of units and conversion here. So 1 bar is equivalent to 10 to the power of 5 kilogram per meter per second square equals to 10 to the power of 5 Newton per meter square. Okay, so you have a different units that you have to address, and you need to know how does the conversion look like. Okay, and then for example, like pressure 1 bar is equivalent to 0.986 atm, equivalent to 750.06 torr, for example. So that is pressure. For volume, for example, like you have 1 meter cube is equals to 10 to the power of 3 liters, and then you have in feet cube, in gallon as well. So this is some of the conversion being given to you. Density, also you have a different units. If let's say you're using AES, similarly with energy, so 1 joule is equals to 1 kilogram per 1 kilogram meter square per second square. This is also equivalent to 1 Newton meter. Okay, so you have other units as well. Similarly with power. Okay, so there's a lot of combination. There's a lots of units that you have to. This is not that difficult, because if let's say you can just Google and calculate, convert, it is easier. But if you want to do it manually, it may take some time in order for you to actually make that particular change. So I have a little bit task here, right? Let's do this. I have about, I'm going to give you for the next 10 minutes, not 5, I think about 5 minutes lah. 5 minutes is faster. Even maybe 3 minutes. So I would like you to actually find out about the unit SI that is being given here. So you can see that when I put dimension here, it's actually length times length is actually L square. So we call it as area. If it length over time is equals to L over T, okay, this is velocity. And if let's say length over time square, it is acceleration. And mass times length divided by times is actually work. Okay, so how about you spend time? Okay, just list down the unit actually related to this. Okay, if you can just do on your own first. For example, like if let's say length times length L square area, so what would be a unit SI in there? Okay, it will be meter square again, right? And then velocity, it will be meter per second. And acceleration, it will be meter per second square. And work as well. Okay, work, what is that? Can you have a guess about the last answer here? So what do you think, what will be the unit for work here? Work is joule lah. Okay, right. So similarly with unit AES, you have the table here. So you need to convert this into the unit AES. So you can refer to the conversion table that I have given earlier in your slide, that you can convert this into the AES unit as well. It's okay. You can just take your turn later. You can do it later. I'm afraid that I might not have time to do this activity with you, but ada few more slides that is coming up. All right. So process system. So it's process and system. Okay, process system, right? Imagine you have a system. Okay, imagine like for example you have okay, let's say you have a bottle. You have a bottle, and then what is inside the bottle is what we call a system, right? And then when the outer layer of the bottle is what we call as the boundary, and outside of the bottle is what we call as surrounding. Okay, so this is the definition of it. Surroundings is the mass or region outside the system. So which is means that if let's say I just define this bottle as my system, so whatever that is outside this bottle is what we call as surroundings. And then a system itself is a quantity of matter or a region in space chosen for study. So I choose this bottle as my space of study. Okay, either I open it or I close it, it is called a system. And then the third one is the boundary, which is the real or imaginary surface that separates the system from its surrounding. Now, because this bottle, it is a bottle, there is a glass bottle, so this is the boundary on it. Okay, but it can also be an imaginary boundary. Imaginary boundary ni macam, if let's say, how do I say? So if let's say, right, for example, like if let's say you switch on the stove, right? There is some heat coming out from the stove, right? So the stove itself is actually the heat that is coming out, the flame that is coming out from the stove. We call it as a system. So because we want to study that system. Whatever that is not the flame, which is surrounding it, we call it as a surrounding. But you cannot see the boundary, okay? But you have to define the boundary itself. So to what extent that you want to see, for example, like the flame, maybe the tip of the flame become your boundary. Okay, you cannot see that boundary, but you can define it as your imaginary boundary. So the boundary itself is something that separates the system from its surrounding. It can also be fixed, it can also be movable. Okay, so in order for you to understand the type of system, okay, it's easy. So again, I took up this bottle, right? This contain of lemon essential oil inside here. And you know the property of essential oil, if I let it open for 24 hours, the next day you can start to see that the oil inside here is dropping. It's no longer being there. So if I closed it, so this is what I call as closed system. Okay, this is closed system because what is actually being transferred here is only the heat. So if let's say I provided, if let's say in this bottle I put some heat, okay, for certain time the heat will dissipate out. It will just leave the bottle, okay. But the mass will not leave the bottle. The mass will be inside there. So this is what we call as closed system. But when I start to open this bottle and I leave it for 24 hours, so there is an energy and mass being transferred from the system to the surrounding or from surrounding to the system because this is open. Okay, so that is the difference between closed and open system. But what about isolated system? Isolated system is where actually there is no energy or mass transfer across boundary. Can you give an answer, an example of what is isolated system? Anybody can share something, can write on the chat. What is the example of isolated system? Do you have any idea? I open and close is easy. Just now, this is closed. Okay, when I open it, and it is open. So if it is open, then there is a potential of the mass being transferred because as I said, this can be actually vaporized out and then convert into something else. But if I close this, it's just there is some energy comes in and out. For example, if let's say this is being heated, so there will be some energy transfer. But isolated system, I think as Adriana pointed out here, like thermosflask. Yes, thermosflask is an example of isolated system where actually there is no energy or mass transfer across boundary. Okay, but of course it is not a perfect isolated system. Perfect isolated system, which means that there is no transfer of energy at all. If it a perfect system, if it a perfect thermosflask, it will still hot until tomorrow. Okay, it will still be hot until 24 days to 24 hours. For the next 365 days, it will still be hot. But of course, there is no perfect isolated system because once you open the thermosflask, you use it. The next day, you pour some hot water. The next day, you can start to see that hot water is no longer hot, right? But that is an example of isolated system. Another example of isolated system is like you have a a pressure a pressure container. Okay, so for example, like you already put some heat inside there, and then you tighten it up. Okay, and then it's in a vacuum condition. So that is also what we call as isolated system. So these are the three things that you have to bear in mind lah about the type of system that we are facing. So as a properties of a system, okay, what is actually property? It is any characteristic of a system. So if let's say you have a system, you need to know about the characteristic of it. For example, like again, we come back to this bottle. Okay, very interesting bottle. You come back to this bottle, so you'll be able to tell the characteristic of this bottle. One of it is actually you can tell what will be the temperature of this, okay, this system. Okay, you have this bottle as your system. You can tell what is the temperature of the system. You can tell what is the pressure of it. You can tell the volume. You can tell the mass of it. But also, you can also tell different other things, okay, such as what is the viscosity of the fluid inside here, what is the thermal conductivity, what is the thermal expansion coefficient, and etc. For example, like these are all some three familiar, I don't know, I'm not sure whether you are familiar with it, but I think the first one definitely you are familiar with. Okay, so what's the first one? That is the density, right? Density. So you can tell the density. That is also a property. This is like specific gravity, which is the density of the fluid with respect to the density of water. And then you can also have specific volume. Okay, so this is actually three. The specific volume is actually the inverse of the density itself. So you have three different equations to represent actually the property of a certain system. Okay, so if let's say you go to look at just a bottle of water, for example, you'll be able to tell how much volume is the water, what is the density of water, what is the thermal conductivity, and so on. Okay, so telling all these characteristic is what we call as property. Classification of property. So there are actually two ways to classify the property. One is what we call as intensive property. Another one is what we call as extensive property. Okay, so what is the difference between intensive and extensive? Right. Intensive property, it is independent of mass of a system. For example, like the temperature and the pressure, it is independent of mass. But extensive is something which is dependent on the mass or the size of the system. Imagine if let's say you have a box here, okay, a cylinder, for example, if you have a cylinder and it contains specific mass, it contains specific volume inside here, it contains, it is in with respect to the certain temperature, with pressure as well as the density, okay. And now you slice this particular box into half, okay. You slice into half. The temperature, the pressure, the density of it does not change with actually when you change the size of it. So this is what we call as intensive property. But when you start to actually slice into half, the mass is no longer the same, no longer m, it becomes half m. How about the volume? The volume also becomes half volume. So this is what we call as extensive property. Okay, so I hope that you can actually start to observe what is the difference between intensive and extensive property. Let's move on to state and equilibrium. Okay. All right. When you are dealing with the thermodynamics, this is actually dealing with the equilibrium states. Okay. And what does it mean by equilibrium? It is actually a state of balance. So for example, like imagine two people who are actually trying to balance themselves on a seesaw. Okay, on a seesaw. It doesn't mean that the seesaw need to be perfectly balanced now. It's just a matter that, for example, like if let's say two people trying to balance on a seesaw for quite some times and it doesn't change at all in terms of the slanting. For example, like they're trying to balance the seesaw like this, for example. Okay. And then when they're trying to balance the seesaw like this, and for quite some times, which means that, and it is perfectly balanced over there at that slant, okay, at that gradient, which means that they have achieved what we call as equilibrium. But when they start to move and it is being disturbed, so it's no longer in the states of equilibrium. Okay, so in an equilibrium state, there are no unbalanced potential or driving forces within the system, which means that if let's say you have an equilibrium, okay, just now, if let's say I have this water bottle, okay, and then it is at 25 degrees Celsius and it is not being moved at all, it's just stay as it is, nothing, and then the surrounding is with the same temperature and so on. So I can say that the water, it is in equilibrium. But when you start to shake it, for example, change it, so the equilibrium here is being disturbed. Okay, so there are several types of equilibrium that we can see. First one is actually what we call as thermal equilibrium. Okay, if let's say the temperature is the same throughout the entire system. Again, look at the example of this water bottle. Just now, I take the cool water, which is at, I would say at 20, let's say we say about 5 degrees Celsius. Okay, the water is 5 degrees Celsius. Maybe more. Okay, maybe more. Maybe it's about like 10 degrees Celsius. And then I put it up here, which is at the surrounding, where my surrounding right now, maybe it is about 27 degrees Celsius, right? So at the moment, when you put this particular water bottle and with this kind of surrounding, it is not in equilibrium state. It will reach an equilibrium state when actually the water inside here have the same temperature as my surrounding right now. So that is where actually it started to reach equilibrium. We call it as thermal equilibrium. Okay. For example, like if let's say you have a closed system, okay, you're pouring several chemicals inside the system and then you close it. And that particular system comes from different temperature, you know. There's a chemical A with 20 degree, 20 other chemical B with 40 degree. And then after a while, they settle down and they become a uniform temperature. So that is what we call as equilibrium. So mechanical equilibrium, it means that if there is no change in pressure at any point of the system with time. For example, here, okay, you have gas in a compressor, in a container. Okay, so you push the valve and suddenly the gas wanted to expand. So it pushed back the valve until at the point that particular valve no longer move. So when it no longer move, then what we can say that that particular system is in equilibrium. It has reached its equilibrium. Phase equilibrium, for example, if a system involves two phases and when the mass of each phase reaches an equilibrium levels and stays there. So if let's say you have two different phases, imagine water and ice, for example. Okay, so if let's say at certain temperature, water and ice, you mix up together, and then the mass of each phase reach an equilibrium. So it's no longer like ice will no longer become water, water will no longer become ice. So that's what we call as the phase equilibrium. It is at equilibrium. And in chemical equilibrium, if the chemical composition of a system does not change with time, there is no chemical reactions occur. Okay, which means that the chemical composition stay as it is. So that's what we call as chemical equilibrium. So there are different type of equilibrium that that we are actually looking at. Okay, processes and cycle. Okay, right. So what is process and path? First thing first, process. Process is a change that a system undergoes from one equilibrium state to another. So for example, like here, there are two types of property. Okay, property A and property B. Property, if you can remember, it is something like temperature, pressure, mass, what else? Density, specific gravity, and so on. That is property, right? Okay, and then so a process is a change that the system occurs from one equilibrium state to another. So if let's say just now you have one state which is at equilibrium, okay, and then when there is a change, it tries to reach another state of equilibrium, and the process, it goes from state 1 to become state 2 is what we call as process path. Okay, as a process path. So path is actually the series of states through which a system passes during a process. Okay, so if imagine, let's say we put this as pressure and this is as temperature, for example. Okay, at state one, for example, temperature, it's already at equilibrium at certain pressure and temperature. But when you start to provide more heat, for example, so temperature increasing, and then because of the system, it's also increased the pressure, for example. So now it arrived at state 2, and it becomes equilibrium again at this particular state. Okay, so this is what we call as and then this is what we call a process that it goes through, and this is what we call as process path that it selects to be. Okay, so you have to remember what is property, what is actually process. And then if let's say you have prefix ISO, it is often used to designate a process for which a particular property remains constant. For example, isothermal process, a process during which the temperature T remains constant. So for example, like if let's say, how do I give an example? You are actually moving one item to another place. Okay, so that is involved no change of temperature happening during that particular time. So we can just simply say this is isothermal process. And if let's say there is no change of volume, okay, we call it as isochoric process. And if let's say there is no change of pressure, which means that when you undergo certain process, there is a change of process, but during that process, there is no change of pressure. Pressure remain constant. This is what we call as isobaric process. And the cycle is a process during which the initial and final states are identical, which means that it completes the cycle. Daripada awal, at the state 1, and then it go to state 2, and then it go to state 3, and then it goes back to state 1. So which means that it goes back to the initial state. This is what we call as a cycle. So you will learn a lot about cycle later, engine cycle, all this Rankine cycle, Carnot engine cycle, all those kind of thing in the thermodynamic course. So these are some terms that you have to hold into lah, right? Even actually the terms like isothermal, isochoric, isobaric is something that you really need to be able to relate to. Okay, let me ask you one thing. If let's say you put water into the kettle, okay, and then you heat up the kettle, right? You heat up the kettle, but at the same time you make sure that the kettle is being closed. Is actually you do not release the kettle, sometimes because when you open this, it is an open system, there is some vapor going out, right? But now you just want to make sure that everything is being closed. You heat a kettle in a closed system lah. Okay, you just provide the heat, so there is no change of mass. So what do you think will be the process then? Is it isothermal process? Is it isochoric process? Or is it isobaric process? Okay, Izzati said it is isochoric process because there is no change of volume, right? Okay, so because we close it properly, there is no change of volume. There is a change of temperature. Temperature definitely change because we heat up the kettle. There is, of course, a change of pressure because when we close the system, the gas inside the kettle is trying to get out. Okay, so it hits the wall of the kettle. So it is not definitely an isobaric process. So it is an isochoric process. Okay. Now, I would like you. I'm going to give you to some breakout activity. So you actually in your breakout rooms. I would like you to observe this process. Okay. In 1 minute, please think what is this process is all about. Is it isothermal? Is it isobaric or isochoric? What happened throughout this process? Okay. And get into your breakout team and share your thought. All right. So I would like to break you out for a while, maybe for the next 5 minutes, so you can actually discuss with every one of you in the team. I have about 90 of you, so I'll divide into 18. Okay. You'll be there in your groups. I hope that you can discuss with each other. And then after that, I'll put up the Mentimeter so you can actually share your thoughts over there. Okay, so we're going to start now, 6:13. I'll broadcast from time to time, so maybe we close back the group by 6:20.
Pagkayado na gun.
Okay, right. So I acknowledge that some of you have not, I think you have not been exposed to breakout sessions. I do anticipate that actually in whenever that you've been given tasks to be in your breakout sessions, that you actually start to talk to each other, or maybe you can chat with each other in a much more closer punya close in a smaller room, smaller number of people, and then you'll be able to start to the what do you call that, share with each other your thoughts, right? Because I know that you use, I think most of the time during the pandemic you used to work all by yourself inside the class. Maybe during the project, yes, you work together, but not inside the class. You to make sure that we actually do the talking to each other, because this is where actually you try to develop your cognitive thinking among yourself. Uh, if you're not participate among yourself, then you'll not be able to get the right thinking process. Okay, so that's why I know that some of you know the answers straight away, but I would like you to go to and validate your understanding about it. All right, so let us see what actually that you have shared here. Okay, it is a isothermal process. Okay, let me see. This isothermal, okay, because pressure increase, volume decrease. So you can see from here. So the graph that you can see from here is what we call as there is a change of volume. Okay, there is a change of volume from V1 until V2. So what is actually this process is all about? We call it as compression. Okay, so we compress. So we compress the valve, push the piston, okay, until it is nearly dah padat lah kan, dah padu kat sini. So this is where actually you push it. So at the initial state, okay, at the initial state, the pressure is low. The pressure is very low because there is a lots of room for the gas to move around, okay, to move around within volume 1. But when you start to compress it to volume 2, okay, this is actually the final state. The gas is starting right now being, is knocking with each other, it's colliding with each other. So when it's still colliding, when it collides with each other, then the pressure is increasing. Okay, so you can see the process is that initially the pressure is low, now the pressure is increased when actually V1, the volume is expanded, and now like it is being compressed. Okay, so this is the initial state, and then this is the final state, and you can have the process part. So this could be an isothermal process. Okay, it is not isobaric, it is not isochoric, because there is a change of volume as well as there is a change of pressure. Okay, what else that you comment here? Let's see. There is a change in internal energy, heat energy, and work even though the temperature remains. Okay. Isothermal, the temperature remains constant as the volume pressure changes. Isothermal temperature remains constant, volume decrease, pressure increase. Process in an isothermal process, the temperature constant in the system. Temperature increase, the volume is decrease. All right, good. Okay. Um, okay, let's talk about quasi-static set. Process proceeds in a manner that the system remain infinitesimally close to an equilibrium state at all times. What it means here is that, for example, when there is a change of equilibrium, okay, there is a change of equilibrium state. For example, initially it starts at this part, and then it slowly move and slowly it goes down, and the distance slowly goes down without being noticed, without you notice it. So this is what we call as quasi-equilibrium or quasi-static process. Okay, sufficiently slow process allow the system to adjust to itself internally so that properties in one part of the system do not change any faster than those at the other parts. For example, at this particular process, there is a change of volume, right? Because when there is a compression, but because it is happening very infinitesimally close to initial equilibrium state, so it reached equilibrium. Um, it the changes too, you will not be able to notice it, but it's actually there is a change of equilibrium state. It becomes very slow. Okay, it becomes very slow, slow compression, quasi equilibrium. But for a non-quasi equilibrium, there is a very fast compression, which means usually we need to put work lah. We need to put work in order for us to compress, to make sure that it is being compressed to this state. Okay, so that is the difference between quasi-equilibrium as non-quasi-equilibrium. Another thinking time for you. Okay, what are the examples that you can think of surrounding you that works under quasi-equilibrium process? And number two, why it is important for an engineer to know about quasi-equilibrium. This is something that I would like to think of. Okay, so if you remember again, quasi-equilibrium, there is a change. Okay, there is a change. There is a process happening. Okay, there is a process happening where the state number one to state number two and the equilibrium change. But it is happening in a very slow process that it is unnoticeable. And this is what we call as quasi-equilibrium. But if let's say you start to actually move it very fast, you push it with your own, and then you move very fast compression, this is no longer called as non-quasi-equilibrium. So my question is, what are the examples that you can think of surrounding you that works under quasi-equilibrium process? Just think of any examples that you can relate to. Anything that happened slowly, infinitely small, such a way that you don't notice. Okay, injection. Okay, what else? What are other examples that you can think of? Growth of plants. Okay. Any other idea? Rock formation. Okay. Syringe. Bicycle pump. Flow of water from a tank through tube. Flow of water from a tank through a tube. Okay. Human lungs. Syringe. The railway line. Rusting. Process of karat. Corrosion. Syringe. Okay. So most of you are thinking about syringe, like, syringe, of course, you need, if let's say you're working on a syringe, if you're not pushing the syringe and it just go by itself going down inside you, for example, that is a quasi-equilibrium. But most of the time, when we do the injection of vaccine, for example, you are pushing it, so you are doing some work there, right? So that is no longer it's no longer called as quasi-equilibrium process. Bicycle pump, yes. If let's say you have you release by yourself, right? You don't actually push it, you don't actually compress it, but from time to time you can start to see that when you lift it up, when you lift the pump, okay, when you raise the bicycle to you bend, and then you and that's what we call as quasi. I'm sorry, sir, I didn't share my screen. Astaghfirullahaladzim. Minta maaf. You should see. But some of you start you watch your slide, right? Sorry, eh. Kejap. Cakap seorang-seorang sonok je kan. Screen tak share. Okay. Okay. So we were talking just now about about this, right? And then the thinking time is actually, why do you think for the engineer to know about quasi why is it for the engineer to know about okay, decrease probability is easy to analyze invention of a machine. Apa ni igloo ni? To improve the innovation, easy to analyze to prevent damages caused by friction, to have more understanding about it, to be able to avoid from the mistake, to know what's happening that might affect an event or project. So you will not be able to make mistake. To apply in certain situation there are needs in application, to apply future problems, invention of a machine, and so on. Because it adjusts itself. Okay. The most important part when actually you know about the quasi-equilibrium, you can make a better estimation. For example, like you when you devise of a certain equipment, you know what will be the maximum output or maximum input and the minimum one, the minimum input and minimum output of the device. For example, like if let's say we talk about the bicycle pump, for example. in order for you to develop the bicycle pump, if you know about the quasi-equilibrium, so how it changed from one, for example, like how it changed from one equilibrium state to another equilibrium state, you know that how much work that you need in order for you to use that pump for pumping the air, for example. If you do not, if you do not know about it, then it causes a lot of force work that need to be done. Then it costs you more actually during your estimation or prediction. So by knowing about the quasi-equilibrium status, so it saves you a lot lah. Whenever that you want to do some kind of invention, okay, you know what's going on, and then you can try to work on the quasi-equilibrium punya state to make it a much more efficient punya process, much more efficient equipment, rather than you are putting a lot of work to make sure that the equipment work. Okay, so that is why we need to know about quasi-equilibrium. Okay. Okay. Some other things that I would like to share with you is what we call as process variables. So process variables ni, this is something that you need to know. For example, about temperature. Temperature is actually to measure the hotness and the coldness of it, and it is a transfer of heat from higher to lower temperature until both bodies attain the same temperature. Okay, so for example, like you go to the shop kan, kita scan kita punya body temperature. It works in a way that it scan our body temperature too, because of the fluid to reach the same equilibrium. Only then it will be able to give us the direct the right numbers lah. What, because the reading of the what do you call that, the reading of the temperature that we have at the shop, for example, we go kan, scanning my sejahtera tu, the reading can only be given until our body reach thermal equilibrium. So kalau body kita tak reach thermal equilibrium with the device itself, okay, it means
你是 unstable 啊？对 unstable。我有 internet connection is unstable。
okay ke tu? Okay. So at that point, heat transfer stops and the two bodies have reached thermal equilibrium. So you have the device, and then our body itself, so when it reaches with thermal equilibrium, only then it can give us the reading, the correct reading. The zeroth law of thermodynamics, okay, they are the zeroth law of thermodynamics. It mentions that two bodies are in thermal equilibrium when they have reached the same temperature. If two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other. Okay, so maksudnya kalau kita ada for example, like there is another third body coming into the system. Okay, we have two bodies in the system, and then it reach equilibrium, and then when there is a third body coming in with different temperature, for example, until it reach the equilibrium, then we are also in thermal equilibrium with each other. Okay, so that is what we call as zeroth law of thermodynamics. There is 4 temperature scales, as you know: Celsius, Fahrenheit, Kelvin, and Rankine. So in Kelvin, it's easier for us to translate. If let's say you want to know the temperature in degrees Celsius, we just take the temperature in Kelvin minus 273.15, then we can get the temperature of Celsius. And then the Rankine is actually related to Fahrenheit. So if you know the temperature, you want to know the temperature in Rankine, so actually the Fahrenheit plus 459.67. And if you want to convert between between the Rankine and Kelvin, so you have to multiply with 1.8. Okay. Similarly, if let's say you want to convert from Fahrenheit to Celsius or Celsius to Fahrenheit, so if let's say you want to know the temperature in Fahrenheit, 1.8 times in degrees Celsius plus with 32. Okay. So you know that the change of temperature in Kelvin is similar with change of temperature in Celsius, and the change of temperature in Rankine is the same as temperature change in Fahrenheit. So if you want to know that, for example, this is some degree of temperature, 1 Kelvin is equals to 1 degrees Celsius, but you have to multiply with 1.8 Rankine. Okay, 1.8 in order for you to get in Rankine, comparison of magnitudes. So for example, right now you have two thermometers. Okay, one thermometers, the absolute zero is given for Rankine, but here this is negative 459.67. So even for Kelvin, this is the zero kat sini, but for degree Celsius, this is already negative 273.15. Okay, so there is some range of temperature, comparison of temperature scales that you can think of. And if you reach 273.16, this is where actually 273.16 Kelvin, this is where actually we reach the triple point of the water. Okay. Pressure pula, as I said, this is actually normal force exerted by a fluid per unit area. So you have different, again, one pressure, you have a different units. If let's say you are using AES or you're using SI, then you have a different units. This is the pressure gauge. This is where actually you will encounter a lot when you are dealing with become a chemical engineer later on. There's a lot of process. Each of these gauge is attached to a cylinder, gas cylinder, for example, gas tank. Okay, so you'll be able to get some reading that is being given to you. Absolute pressure. So there is a different type of pressure here. There is an absolute pressure, gauge pressure, as well as vacuum pressures. Okay. Absolute pressure is actually the actual pressure at a given position. It is measured relative to absolute vacuum, okay, which is absolute zero pressure. But for the gauge pressure, it is the difference between the absolute pressure and the local atmospheric pressure. So most of the time, if you are reading the gauge kat sini, okay, it will just give you, for example, like it's pointing here at 100. So you get 100 PSI kat sini, bar kat sini. If let's say this is 6.2 bar lah, we take the reading internal, okay, 6.2 bar. So 6.2 bar, this is only what we call as the gauge pressure. So in order for us to know what would be the pressure absolute, so we have to add on with atmospheric pressure. So the pressure absolute for this gas is actually 6.2 plus 1 bar, which is 7.2 bar. So this is the formula for us to calculate what is gauge pressure, as well as we can also use this for the vacuum pressure. Okay. And the vacuum pressures, it is the pressure below the atmospheric pressure. So throughout this course, thermodynamic ni, you will denote P as absolute pressure unless it is specified otherwise. So in order for us to calculate absolute pressure, it is simply by atmospheric pressure plus with the gauge pressure. Okay, that will give you absolute pressure. So in this particular graph, you can see that this particular magnitude line, it is absolute pressure. But in order for us to get absolute pressure, it is an addition between atmospheric pressure plus with the gauge pressure. So at the bottom line here, this is what we call as absolute vacuum. So similarly here, if you have an atmospheric pressure, okay, and this is the below the atmospheric pressure, and you want to determine the vacuum pressure. So actually the absolute pressure, okay, atmospheric pressure minus with the absolute pressure, you'll get the vacuum pressure. Okay.
Ada promosi dalam ego tu ke?
Just a little bit more. I think about 4-5 slides, but I think I can go quickly with this. It's not that you just need to know, and then you can read further on your own. It's actually the first one is the variation of pressure with depth. What it's trying to mention here is that, okay, in order for you to determine the pressure, if let's say you have a distance delta z, okay, z1 and z2 is actually the different in height, the different in the distance, okay, and then you have a system here, you have a free body diagram kat sini, a system here. Then in order for you to determine what will be the pressure, the change of pressure between state P1 and P2, okay, this is the line for P2, this is the line for P1. So it's simply just P2 minus P1, or you can just equals to rho. Rho is the density, gravity, okay, times with the gravity, times with the change of height. between Z2 and Z1. So this is why actually rho G delta Z. Okay, rho G delta Z. And then you can have the pressure is equals to atmospheric pressure plus rho GH, or the gauge pressure is actually equals to rho GH. But, okay, there is a but as well. If let's say you have a system, in a system where there is a change of density. So there is a change of density from one point to another, okay? You need to do some kind of integration, okay? Because there is a variation of density with elevation is known. So you need to do some integration from point 1 until point 2, rho G dz. So this is how you can calculate the change of pressure. Among the other things that we have to bear in mind is that, for example, like you are looking at the sea level, for example, okay, the sea level. This is what we call as atmospheric pressure, PATM. When it goes down below the sea, so the pressure is actually increasing, okay? So the pressure at the bottom here is much higher than pressure at the top here. If let's say you imagine a sea or a river, so the surface of the river is actually what we call as atmospheric pressure. And then when it goes down below further, then the pressure is actually increasing. So the pressure below, in order for you to determine the pressure below, you need to add pressure atmosphere plus with the rho GH, which means that you have the density of water, for example, multiply with the gravity and multiply with the height difference. So that's where you can get the pressure below. Similarly here, if let's say you have a room just in your own room, right? You have a top ceiling as well as the bottom. Actually, it is a negligible, with even with certain height, it is negligible. If let's say you just have a room on your own, okay? Because the change of temperature, you can just say this is 1 atmospheric pressure. Another condition is where actually you have several points here, A, B, C, D, E, F, G, for example. So you can see that it is actually at a similar level and it is within the similar fluid, okay, water, which is water. So at this particular point, the pressure are all the same. So pressure of A equals to B, C, D, and so on. And in order for us to calculate at any point of this, the pressure is, we just need to know the height. So we add on atmospheric pressure plus with the rho GH of this height. However, if you go to down to I, so the height change is different. But at the same time, when you look at I and H, because H is right now have a different fluid, which is mercury, so you need to calculate separately. So the pressure at this particular point H is not the same as pressure at I, okay, because it has two different fluids. So that is, I think, one of the important things that you have to bear in mind. Okay, for the Pascal law, you can also look at the Pascal law. That is, the pressure applied to a confined fluid increases the pressure throughout by the same amount. So imagine this, we have learned in physics before, okay? So for example, like if let's say you have a very small diameter area, okay? You have, and then the F1 is equals to P1 multiplied with A1, which is pressure, multiply with the area. So this is the area multiplied with the pressure. And for F2, it is P2 multiplied with A2. Okay, there is another larger area, but it gives you F2. So what we can say that the ratio between F2 over F1 is equals to A2 over A1. This is what we call as ideal mechanical advantage of the hydraulic lift. So this is why actually only a small device can uplift a big car, for example, because it actually applies to the same pressure. It has similar pressure. Okay, so when you apply the car jack, for example, car jack is very small. You just jack it up, you can jack a car and car will be uplifted. Okay, and then this is being lifted up by what we call as hydraulic lift. So lifting of a large weight by small force is the application of the Pascal's law. And then I would like you to read through. There is some devices that you can use for pressure measurement. For example, you can use manometer. Okay, the manometer is actually, for example, like if let's say you want to measure the point of at this particular point, you need to add on, because there is a different fluid, so you need to calculate separately. So you need to know the distance, the height between at this point to the height 1, so that before it reach the fluid number 2, and then you need to know H2, and then you need to know H3 as well. So you can plus add on with the atmospheric pressure, then you can get the pressure at this particular point. So for the basic manometer, again, if let's say you have a gas, okay, you have the gas, and then the gas is pushing the fluid here. So when the fluid is being pushed, if let's say they push up to this point, so you take from 1 until 2, and then you take the height. Okay, so in order for you to know the pressure 2, because of the gas is introduced, you just need to add on atmospheric pressure plus the with rho GH. Because you just need to know the height of this, then you can actually calculate the pressure of this particular gas. Okay, and in order for you to determine what is H, it depends on where the fluid will stop. If let's say the fluid goes higher, then this is your new H lah, right? This is also different type of devices that you can use. Border tube, pressure transducers, strain gauge pressure transducers, piezoelectric transducers. So there are many other mechanisms that you can read on later lah. I mean, I think that is something that you can learn and understand later. Okay, I know that 2 hours is very tiring. So next week I try to actually compress it. I try to make it 1.5 hours, the max in terms of the slide, so we can actually cut some unnecessary things. So I can give you something that you can read on your own later. So let's recap what have you learned today. Can you share with me? Any new thing, any interesting facts, something that is actually triggering you? So what are the things that you might have learned today? Can you share with me before we ended the session? I'll give you another document later on some of the examples of certain calculation, simple calculation that you can use from pressure, temperature, and so on.
Tahu tengok gua dia.
Macam mana dia orang duduk dulu.
Ilmu yang bermanfaat.
Dia dia.
Okay.
Gara buat macam situ. Kita video hang ni. Kalau edit tak mau ada tak boleh. Dia baca. Betul sih.
So pressure too is something that is towards the end. So I think you remember more about pressure. Okay. So you learn about isothermal. I think the equilibrium keywords is also there. Temperature. You learn about isochoric, isobaric. Okay. We learn about the okay. You learn about quasi-equilibrium. What else? SI units, unit and dimension. I think one of the things that I think some of you highlighted here, process. The word process, the word property is something that you have to remember as well. Okay, the keyword of the process and property is something that you have to recall. You have to get to know about that as well. Process, and then you need to know about cycle. Cycle is something that is also you need to know. Okay, and then you need to understand. Those are the process that I have mentioned to you. Okay. All right. Any questions before we leave? I think that we have come very long. I think it's nearly 2 hours. Inshallah, next week I'll try to cut it short. I also become tired lah. About for 2 hours non-stop talking, but a bit tiring. So I'll try to cut it short, 1.5 hours. But thank you very much for your attention. I think you will stay with me until about 2 hours. So I think I'll see you next week. Okay. Right? So next week, next Tuesday again. Take care everyone. Okay. Hope kalau jumpa saya, tegur saya lah. Saya tak apa nak kenal lagi you all semua kan. Right? Take care. Assalamualaikum warahmatullahi wabarakatuh.
Doctor, what about attendance?
Yeah.
Oh, ada tadi form mana tadi? Tak nampak link. Tolong isi attendance. Okay. Bye-bye. Assalamualaikum. And good evening.
Thank you, Prof.